Good day to the viewers of this video. I am Rayleigh and today I'm going to demonstrate a simple batch distillation calculations of one of the problems in Chapter 9 of Separation Processes Engineering by Philip Pongkat. To start, let's read the problem. Problem D5. A simple batch distillation is being done to process a feed containing water and n-butanol that is 52 mol% water. The feed to the still pot is 3.0 kmol. The final still concentration should be 28 mol% water. The equilibrium data are in table 8-2. First A, find the final amount in the still pot, the total amount of the distillate vapor collected, and the average mole fraction water in the vapor distillate. Next, after the distillate vapor is condensed in the total condenser, the liquid is sent to the settler. Two distillate liquid products are withdrawn. Find the total amounts of each distillate liquid collected, the D1 having a mole fraction of water 0.573 and D2 with a mole fraction of water 0.975 in kilomoles. The first thing that we're going to do is to create a visualization of the indicated problem through the schematic diagram. Here, the still pot contains a feed of 3.0 kilomole mixture of n-butanol and water, which has a 52 mol% water. Then from pubchem.gov, we were able to determine that n-butanol has a higher boiling point, which means that it is less volatile than water, as 1-butanol has a boiling point of 117.6 degrees Celsius. Hence, in this calculation, the basis is the component water. Then QB, the heat introduced in the still pot, increases the temperature of the still pot, causing the more volatile component water to evaporate. Then the evaporated water goes to the condenser where heat is removed, QC. The distillate is then collected with a higher concentration of water than n-butanol. For part A, the requirements are the final amount in the still pot denoted as W, the total amount of distillate vapor collected, dV total, and the average mole fraction water in the vapor distillate, YD average. Step 1. We're going to establish the equation to use. Rayleigh equation is derived from the mass balance, which is rate input is equal to the rate output assuming no accumulation in the process, and component balance, which is instantaneous rate of depletion in the still, is equal to the instantaneous rate of output. It should be noted that the distillate rate and the depletion rate in the still is dependent of the rate of heat input in the still. Hence the equation natural logarithm of the final amount in the still pot divided by the feed is equal to the integral of dxw divided by the average mole fraction in the distillate minus the final mole fraction in the still pot evaluated from xw0 to xw. Then for step 2, we solve for the integral part of the Rayleigh equation using 1/3 Simpson's rule. The 1/3 Simpson's rule is the integral of function of x from a to b is equal to the delta x divided by 3 times function of x as x is equals to a plus function of x as x is equal to b plus 4 times the summation of function of x where x is equal to 2n minus 1 meaning odd plus 2 times the summation of the function of x where x is equal to 2n, meaning even. We don't have the equation to use in the 1/3 Simpson's rule yet, but we were given the equilibrium data in table 8-2. Hence, we can use this to solve for the 1 divided by y minus x, then plotting it in the graph in Excel. So the table 8-2 has a x, y, and the temperature data. So this is a TXY data. Then plotting the 1 divided by y minus x versus x, we're able to generate a graph. This is the graph. Then getting the trend line of the graph using a power of 3 in the polynomial. The equation of the line is y is equal to negative 120.55 x cubed plus 141.2 x squared minus 37.358 x plus 3.9833 with an r squared of 0.4109. Then getting this equation, we can now use the one-third Simpson's rule. In step 5, we get the constant in the equation to make the calculation easier. Then we identified a number of iterations to do in this calculation. So we have a 10 iteration with a lower boundary of 0.52 and an upper boundary of 0.28. Hence, our delta x is 0.024. Shown here are the values using the different value of x. So the function of x as x is equals to a is 5.78733. Then for function of x as x is equal to b, 1.94683. Then the different iterations. Next, we add all the odd iterations and the even iterations. Then using the equation for the one-third Simpson's rule, we can now determine the area under the curve. Therefore, the area under the curve between 0.28 and 0.52 is 0.936. Then recalling the Rayleigh equation, we already determined the integral part of the equation, so substituting that, then raising the whole equation to the Euler's identity to eliminate the natural logarithm. Then from the given, the feed is 3 kilomoles. So 3 kilomoles times 0.3922, we were able to get a final amount in the still pot of 1.1766 kilomole. To determine the total amount of distillate vapor collected, we can do an overall mass balance. So the feed is equal to the final amount in the still pot plus the total amount in the distillate vapor. In the previous calculation, we were able to calculate for the final amount in the still pot. So substituting the values, the total amount of distillate vapor collected is equal to 1.8234 kilomole. Then for the calculation for the average mole fraction water in the vapor distillate, we can use a component mass balance of water. So XW0 times W0 is equal to XW times W plus YD average times DV total. Then from this equation, the only unknown is the YD average. So calculating, we were able to get a value of 0.6749. Therefore, from part A, we were able to determine these values, the final amount in the still pot to be 1.1766 kilomole, the total amount of distillate vapor collected to be 1.8234 kilomole, and the average mole fraction water in vapor distillate to be 0.6749. For part B, we're going to solve for the two distillate liquid products withdrawn, D1 and D2. having a mole fraction of water equal to 0.573 and 0.975 respectively. First, we're going to do a mass balance of water in the distillate. dV average is equals to D1 plus D2. This dV average is the one that we had computed in the part A. Hence, we can rewrite the equation to get the equation for D2. Next, we will do a component balance of water in distillate. YD average, D average is equal to XD1, D1 plus XD2, D2. Then substituting for the values, we are left with an unknown value D1 and D2. Using the equation from the mass balance, we equate the D2, then we were left with the unknown value D1. Solving for D1, D1 is equal to 1.2815 kilomole. Then using the equation from the step 1 mass balance of part B, D2 is equal to 0.5419 kilomole. In summary, we were able to calculate for the final amount in the still pot, the total amount of distillate vapor collected, the average mole fraction water in the vapor distillate, and the two distillate liquid products. And that's all for the simple batch distillation calculation. Hope you learned something. Thank you and have a nice day.